I welcome you all to the course of heat transfer. In today's session, we will discuss a topic heat exchange between non-black bodies. The analysis of radiant heat exchange between non-black bodies is based on following assumptions. The first assumption is the surfaces are arranged at a small distance from each other and are having equal area, so that practically all the radiation emitted by one surface falls on the other. The second assumption is that the surfaces are at uniform temperature and the reflective and emissive properties are constant over all the surface. Third assumption is that the surfaces are separated by a non-absorbing medium such as air. Now, from the first assumption, it is clear that the areas of two non-black surfaces is same. From the second assumption, we can say that either emissive properties or reflective properties will remain same all over the surface. The upper half surface may be having an emissivity of epsilon 1 for surface 1. The same will be there for the bottom half. Similarly, if alpha 1 is the absorptivity for surface 1 for the upper half, same is the case with the other half. And third assumption gives us there should be a non-absorbing medium between these two. It means whatever is emitted by surface 1 must reach to the surface 2. Now, if you consider two parallel non-black surfaces, let us denote them by numbers 1 and 2 corresponding to surface 1. The radiant energy emitted be capital E1. Similarly, from surface 2, the radiant energy emitted is capital E suffix 2. Let alpha 1 is the absorptivity corresponding to surface 1. Alpha 2 is the absorptivity corresponding to surface 2. Epsilon 1 is the emissivity of the surface 1. Similarly, epsilon 2 is the emissivity corresponding to surface 2. The area A1 and A2 are equal to A. Now, in first case, Let us consider the radiant energy E1 is emitted by surface 1 towards surface 2. Now, out of this emitted energy, surface 2 will absorb certain amount of energy and reflects the remaining energy. Now, how much is absorbed by the surface 2 is nothing but absorptivity multiplied by the total energy emitted by surface 1, which is E1. Now, the amount of energy absorbed by surface 2 is nothing but alpha 2 into E1. Now, what is re-emitted by surface 2 towards surface 1 is nothing but 1 minus alpha 2 multiplied by E1. To give you clear idea, let us consider E1 is 100%. Now, out of 100%, how much is absorbed? Alpha 2 times of E1. Now, alpha 2 is, let us consider, say 15%. Now, 15% of 100 is absorbed. Remaining is 85. Now, 85% of energy is re-emitted from surface 2 towards surface 1. Now, again, surface 1 is also having some limitation. Surface 1 can absorb only alpha 1 percentage. Now, out of what energy? 1 minus alpha 2 multiplied by E1 percentage of energy. It can absorb only alpha 1 portion or alpha 1 percentage of energy. Now, on reaching the surface 1, it can absorb alpha 1, which is the absorptivity of the first surface. So that much only it can absorb. Out of what energy? 1 minus alpha 2 into E1. Now this much energy is absorbed because we have defined absorptivity as the amount of energy that is absorbed when we have exposed a surface to the incident radiation. If you take the ratio of amount of energy that is absorbed to the incident radiation, that we call it as absorptivity. Now what is remaining? It is nothing but 1 minus alpha 1 into 1 minus alpha 2 times of E1. Now this process goes on. Now if you calculate the amount of radiant energy which will leave the surface 1 per unit time, it is nothing but E1 minus of alpha 1 into 1 minus alpha 2 into E1 plus alpha 1 plus 1 minus alpha 1 into 1 minus alpha 2 its square into E1. It keeps on increasing, but it will be less than the energy radiated from the first surface. Now, if you write an expression considering the following situation, you will have an expression like this. Now, out of this, if I take alpha 1 into 1 minus alpha 1 into E1 common from the expression within the square bracket, you will left with 1 plus 1 minus alpha 1 into 1 minus alpha 2 plus 1 minus alpha 1 x square into 1 minus alpha 2 x square plus so on. Now if you see the pattern, it is repetitive as well as it forms a series. Now you have a series wherein if you substitute the value of 1 minus alpha 1 into 1 minus alpha 2 as p, you will have a series of 1 plus p square plus p cube plus p to the power 4 plus so on. Now this is nothing but the expansion of the term 1 minus x whole to the power minus 1, or 1 divided by 1 minus x. We have studied this in mathematics. If it is 1 plus 2x plus 3x squared plus 4x cubed, it is an expansion of 1 minus x whole to the power minus 2. Or if it is of this form, 1 minus x plus x squared minus x cubed plus x to the power 4, so on. It is an expansion of 1 plus x whole to the power minus 1, or 1 divided by 1 plus x. If you have 1 minus 2x plus 3x squared minus 4x cubed plus so on, it is an expansion of 1 divided by 1 plus x whole square, or 1 plus x whole to the power minus 2. Now out of this, we have a format of 1 plus p square plus p cube so on. Corresponding to this series, we have 1 divided by 1 minus p. So if you expand this, you will have the terms like 1 plus p square plus p cube so on. Now if I replace the series 1 plus p square plus p cube so on by 1 divided by 1 minus p, I will be having q1 is equals to E1 minus alpha 1 into 1 minus alpha 2 into E1 is taken out, and the series is written as 1 divided by 1 minus p. Now if you take E1 common, you will have expression q1 is equals to E1 into 1 minus of alpha 1 into 1 minus alpha 2 divided by 1 minus of 1 minus alpha 1 into 1 minus alpha 2. Now from Kirchhoff's law, we know that emissivity and absorptivity of a surface are equal, provided they are in thermal equilibrium with surroundings. If a body is in thermal equilibrium with surrounding, then absorptivity can be equated to emissivity. Now we have considered a uniform temperature of the bodies. Hence, Kirchhoff's law can be adopted. Now in place of alpha 1 and alpha 2, I can replace epsilon 1 and epsilon 2. That is the meaning. Now if I do so, I will be having expression Q1 is equals to capital E1, which is the radiant energy emitted by surface 1, multiplied by 1 minus, in place of alpha 1, it is epsilon 1 into 1 minus epsilon 2 divided by 1 minus of epsilon 1 into 1 minus of epsilon 2. Now if you simplify, you will have final expression as capital E1 into epsilon 2 upon epsilon 1 plus epsilon 2 minus of epsilon 1 into epsilon 2. Now this is the energy emitted by surface 1 in terms of emissivities of both the surfaces. Now similarly, if you consider the surface 2, which emits a radiation of emissive power E suffix 2 towards the first surface, which is having epsilon 1 as the absorptive power. Now epsilon 1 into E2 is the amount of energy absorbed. What is remaining? 1 minus alpha 1 multiplied by E2 is reflected back on reaching surface 2. It will absorb alpha 2. So alpha 2 into 1 minus alpha 1 into E2 is absorbed. Then the remaining is 1 minus alpha 1 into 1 minus alpha 2 times of capital E suffix 2. Now this process again goes on continuously. With the knowledge acquired so far, we can again write Q2 is equals to E2 into emissivity of the first surface divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2. Now, the net heat flow from surface 1 to 2 in a unit time is nothing but Q1 on 2 is equals to the difference between Q1 and Q2, which is given by E1 into emissivity of the second surface divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2 minus of E2 emissivity of the first surface divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2. The denominator remains the same. Now if you take the difference, we'll end up with an expression E1 epsilon 2 minus E2 epsilon 1 upon epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2. Now, we know that the emissive power is nothing but epsilon 1 into Stefan-Boltzmann constant into corresponding temperature to the fourth power. So if we replace E1 and E2 as epsilon sigma into T to the power 4, you will have an expression epsilon 1 into sigma T1 to the power 4 into epsilon 2 minus epsilon 2 sigma T2 to the power 4 into epsilon 1 divided by epsilon 1 plus epsilon 2 minus of epsilon 1 into epsilon. Now if you simplify, we'll have a final expression as F1 on 2 into sigma B T1 to the power 4 minus T2 to the power 4, where F1 on 2 is called as interchange factor, or it is also called as equivalent emissivity. equivalent emissivity is given by 1 over 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Now, we also need to discuss little about shape factors and its properties. I have already discussed the definition of shape factor. It is nothing but the fraction of radiative energy that is diffused from one surface and strikes the other surface directly with no intervening reflections. It is denoted by letter F. F1 on 2 indicates the amount of energy radiating from surface 1 and striking the surface 2. To mention some of the properties of the shape factor, it is also called as V factor. Some authors refer this as geometric factor, but all are same. To give you a simplified answer or the definition to the shape factor, if you stand on a surface and if you emit a radiation, how much part it will fall on the same surface? The answer is 0. Because on a flat plate, the surface does not see itself. Hence, the fraction of energy radiating from surface 1 and falling on the same surface is 0. That is why, if you consider a plane surface or a convex surface, in case of convex surface as well as plane surface, F1 on 1 will be equals to 0. Whereas in case of concave surface, F1 on 1 will not be equals to 0 because some part of energy can be absorbed in case of concave surface. Whereas in case of convex surface, it is not possible. Similar is the case with plane surface. Next, shape functions is a function of geometry only. If two bodies exchange heat between them, then it will follow the reciprocity theorem, which states A1 F1 on 2 is equals to A2 F2 on 1, where A1 is the surface area for the first phase, A2 is the surface area of the second surface, F1 on 2 is the fraction of energy emitted by first surface striking towards the second. Similarly, F2 on 1 is the fraction of energy that is emitting from second surface striking towards the first surface. Now, if a surface is completely enclosed by a second surface, say A2, the first surface is being A1 and the second surface is being A2. A1 is completely enclosed by surface A2. And if A1 does not see itself, suppose it could be a convex one, then F1 on 1 is 0. It means F2 1 on 2 will be equals to 1. because the sum of shape factors will always be equals to 1. Suppose there are n surfaces that are taking part in radiation, then F1 on 1 plus F1 on 2 plus F1 on 3, so on up to F1 on n is equals to 1. If F1 on 1 is 0, then sum of remaining shape factors must be equals to unity. Now let us consider an example. Suppose you have a sphere in a cube. The sphere is inside surface. We will designate it as 1, and cube is outside surface. We will designate it as 2. What is F1 on 2 if asked? Obviously it is 1 because F1 on 1 is 0. On a convex surface, the V factor is 0 because it cannot see itself. The radiation emitted by it cannot fall on the same surface. Hence F1 on 1 will be 0. But we know that F1 on 1 plus F1 on 2 should be equals to 1. If F1 on 1 is 0, F1 on 2 should be equals to 1, considering two surfaces. If there are three surfaces, F1 on 1 is 0, F2 on 1 plus F1 on 3 should be equals to 1. I hope you have understood the assumptions as well as the properties of shape functions. This kind of questions will generally be asked in GATE exams as well as many competitive exams. We will discuss some problems on shape functions. With this, I will stop here.